Esther Mullens, a postdoctoral research associate at the South Central Climate Science Center at the University of Oklahoma in Norman. In this video, I'll introduce statistical downscaling. The idea of downscaling is to translate the information we get from the global climate models to local and regional scales. Global climate models themselves typically provide climate data over very large grid points, often 100 to 300 kilometers in size. That's not going to be of much use to most planners who work on much more local scales. Using statistical downscaling, we can get the needed data. Most statistical downscaling approaches begin by comparing global climate model, or GCM, output for a particular time period in the past with observations during that same time period. By comparing model projections and actual climate observations, researchers can see relationships between global and regional climate patterns and describe these relationships using statistics. The next step in the process is for researchers to apply these statistical relationships to future climate projections. Assuming that the statistical relationships observed in the past will continue to hold in the future, researchers can project changes at the regional level based on GCM output. There are several ways to build the statistical relationship I just described. These techniques generally fall into three categories: transfer functions, weather typing, also known as pattern classification or analogs, and weather generators. Transfer functions are often the simplest statistical downscaling methods. They include techniques such as the delta method. The delta method determines the projected change, or delta, of a climate variable from the global climate model and applies it to the observations. For example, let's say I'm concerned about changes in average temperature in Oklahoma. If I use the delta method, I would look at the projected change of temperature from a GCM and apply that change to the observations in Oklahoma to examine what temperatures may look like under a changing climate. Other transfer functions include regression-based techniques. These build a statistical relationship between GCM output, or predictor, and the observations, or predictand. For example, GCM temperature may be used as a predictor for observed temperature during the historical period. The statistical relationship built between the GCM temperatures and observed temperatures can be used with future projections from GCMs to determine how large-scale changes may transfer to local areas. All transfer functions have one aspect in common. They build a direct relationship between the observations and GCM for the same region. Weather typing, or analog techniques, are another method of statistical downscaling. Unlike transfer functions, weather typing uses the large-scale atmospheric patterns from a GCM to build that relationship with observations. Here's an example. Imagine that you collected 30 years' worth of daily weather maps for the South Central United States. These weather maps cover all kinds of varieties of conditions. We classify some as dry days, some as wet days, and some as higher than normal temperatures or lower than normal temperatures. Now let's retrieve the observations from the weather station at Norman. We can now link each individual weather map to a corresponding observation from our weather station during a historical period. Once we determine this link, we compare the future maps that we collected from the GCM to the historical maps. Much like a grand game of picture matching, each future map is matched to a corresponding historical map. Then, since we already know the relationship between the historical map and the weather station, we can assign the GCM the corresponding values from the weather station. We repeat the process until all the future maps are classified, allowing us to collect a full time series of downscaled data. Weather generators are quite different from all the methods of statistical downscaling we've discussed so far. Rather than relating specific events and locations between the GCM and the observations, as transfer functions and weather typing techniques do, weather generators use the projected change to the statistics of climate produced by GCMs to influence the statistics of the historical observations to what they may look like in the future. What do I mean by statistics? I mean things like average daily rainfall or the probability of a rainy day following a dry day. A weather generator would take the projected change in mean temperature from the GCM and modify the mean temperatures of the historical observations at a local scale to figure out what the mean temperature of the future for this area might be. These changes to the statistics are used to create multiple realizations of the future. What are these realizations? They are a time series of the variables of interest, like temperature or precipitation. Each realization will unfold differently from another, but they share the same set of statistics in the future. As with dynamical downscaling techniques, there are several advantages and disadvantages to statistical downscaling. Here are some advantages to statistical downscaling. First, statistical downscaling doesn't take a lot of intensive computer power and can typically be performed on one computer or a small server, while dynamical downscaling often requires multiple servers and supercomputing. The relatively inexpensive nature of statistical downscaling makes it easier to downscale more GCMs than dynamical downscaling. Typically, a statistical downscaling technique can easily downscale 20 GCMs, while dynamical downscaling may only use 2 to 4 GCMs. Second, statistical downscaling can be flexibly crafted for a specific purpose. Let's say you're really interested in potential impacts of climate change in Oklahoma. Statistical downscaling does make it simple to craft a relationship and downscale to capture specific features of interest just for that region. That makes it simple to get information about change specific to your region. Third, statistical downscaling incorporates historical information. Observations are a key part of statistical downscaling, and those observations provide information on past events in a region of interest. Therefore, when statistical downscaling is performed, historical knowledge about local gradients and climate variables can be retained. As with any downscaling technique, there are also disadvantages. First, statistical downscaling requires a long observational record to build robust statistical relationships. How long? At a minimum, this is usually 20 years of data. More commonly, it is more like 50 years or more of data. This requirement can be met easily for temperature and precipitation, but there are fewer observations available for things like evapotranspiration, solar radiation, and humidity. This is a weakness if you are interested in changes to things like soil moisture, since most statistical downscaling techniques focus on those variables with a long observation record. Second, statistical downscaling assumes that the relationships described will be valid in the future. The relationships between observations and GCMs are built during a historical period, such as years 1950 to 2000. It's assumed that these relationships will remain the same in the future. This assumption is called stationarity. This particular assumption may not be valid, particularly close to the end of the century, given that climate change may alter the way the climate currently functions. Third, results from statistical downscaling can be affected by the errors of the GCM. Like dynamical downscaling, statistical downscaling does depend on the GCM information being reliable. If the GCM has errors in a particular region of interest, those errors can be translated to the results of statistical downscaling. At this point, someone studying impacts may ask, which one is the best? That's a lot like asking a car dealer, which one is better, this sedan or this minivan? The GCMs and downscaling techniques all have their strengths and weaknesses, and the best option to use depends on the application. Although no statistically downscaled dataset is perfect, decision makers can use a group of these datasets to examine the range of possible climates they might face in the future. For further help making use of downscale projections, feel free to contact institutions like the South Central Climate Science Center. We're here to help.